Hello everybody. Today I'm going to talk to you guys about thermal energy. Thermal energy is another kind of energy, so now we have three kinds. We have kinetic energy, which is energy of motion, and we have potential energy, which is energy stored for later motion, and then we have thermal energy. Thermal energy is what you might commonly call heat, but heat has a very special meaning you may have learned in chemistry. Heat is actually the transference of energy. So heat is kind of a process. It's a verb, not really a noun. The noun part of that is thermal energy. And so we're going to explore that a little bit today. Thermal energy is what we get when friction robs some kinetic energy from the motion of an object. And so we end up having that kind of transference between one thing and another. We have a process called heating. And so that's one way that we can get some heat. So we're going to talk about this here real quick. Thermal energy. Up until now, we've been talking about motions of large particles. So let's say we have a table or something like a lab station, and we have a box, and that box moves from this position to that position right there. So that's its delta x. And it does so by a force being applied to it, and that's its F right there. And so, as you can see, we've got work being done, and because the work is being done, something is changing about the object. And so either the object is storing that work for later motion, or it's moving itself now, which means we have kinetic energy. And so as a result, we have this work becoming a certain kind of large-scale energy. What happens, though, in the surface between the two, and this is what this diagram right here is trying to show, is that as the surfaces slide past each other, the particles in one surface and the particles in another surface collide. And as you imagine, when they collide, it causes them to move more. And as a result, those tiny little collisions rob motion from the overall object. And so they take the motions of the particles, not the whole object itself, but the particles that make up the surface that is in contact with the other surface, and they cause them to move in a larger way on average. And so there's three kinds of particle motion you may have learned in chemistry. There's vibrational motion, which is either a back and forth vibration around a central point, or in molecules' case, it's kind of a vibration outward and inward for the bonds. You also have rotation, and so rotation is obviously when a particle or a molecule rotates around an axis. Now, vibration is typically what you would see in a solid. Vibration and rotation typically is what you might see in a liquid, and then there's a third kind, and that's translation, where an object moves, or a particle, like an atom or a molecule, moves from one place to another, which is what you might see in a gas or a plasma. And so, actually you could see any of these three in a gas or a plasma, and would see all of them. So particles end up moving more, and on average, we say that their average motion, their average kinetic energy of the particles themselves, is what we measure as temperature. So I'm just going to point this out right here, right there. When you measure the temperature of something, what you're really doing is, in a macroscopic way, in a large-scale way, you're trying to find what the average kinetic energy of the particles that make up that object or substance are. And so the more you have of vibration, or rotation, or translation, if it's a gas or a plasma, the more of that you have, the higher the temperature. The less of that you have, the lower the temperature. And so we're going to see in the next video that there should be a temperature, which we're going to call 0 Kelvin, which is also called absolute zero, which we are going to say is the theoretical point at which we take all of the particle motion out of a substance or an object. It's theoretical because you can't really get there. So we'll talk about that in the next couple of videos, though. Anyway, back to this. So we use friction purposefully to try to heat something up when we strike a match. We can't really see that there. So striking a match right here on the box itself the box has a high friction surface, and so it increases the temperature of the particles inside the match head, which then increase their temperature to the point where they can ignite. And that's how match head works. That's why striking it on some surfaces works to heat it up and to ignite it, and on other surfaces it does not, because there's not enough friction. If you're a Boy Scout, you may have tried this trick, and I have to admit I've tried it and not been successful at all, not even to get it to smoke a little bit. If you take one piece of wood and bore out a hole in another piece of wood, and then rotate this quickly, this first piece of wood, very, very quickly back and forth, the kinetic energy of this rod that's vertical here can be converted into enough thermal energy to cause this to ignite. So you're basically heating up the wood past its ignition point, which I have never been able to do. I think is pretty darn close to magic, it seems like, because I've never even come close. But that is what it is. Anyway, what you can imagine then is, because kinetic energy is robbed from the system and converted into thermal energy, you end up with a system that looks kind of like this. So you're trying to put in some work, and you want it to produce some kinetic and potential energy over here. But as a result of friction, you get this detour of some of the energy into thermal energy, which we signify with a Q for reasons I have no clue about. Can't be a T because that's temperature, so we have to use some other letter, and so we use Q. Q's not being used for anything anyway. So some of the work that you put into the system either becomes kinetic or potential energy, and that would be useful, or it becomes thermal energy, and that's really not useful. And so this is why this is not useful here. This is why we have a distinction between thermal energy and what we normally call mechanical energy. And so this is the mechanical energy up here, which I think was the topic of the last video, right there. So this is not useful, so it's not mechanical energy. And it's all because of that friction. And so when you're thinking about this, the amount of work that you put in is actually the sum of all the kinetic and potential energies plus all the thermal energy. And so anytime you're adding energy to a system or adding work to a system, you end up getting some of these three types in the real world. Hopefully that makes sense. If you have any questions, go ahead and let me know. Thanks for watching.